On October 24, 2025, at 4:10 in the morning, a radio telescope in South Africa caught a signal that should not have been possible. Two precise chemical fingerprints, traces of interstellar water broadcast from a visitor just 3 degrees from the sun. This was not human-made and not a message, but the first ever radiochemistry from an object beyond our solar system. How did a fleeting blip on a crowded frequency become hard proof of water from another star? And what else might be hidden in that signal at 3:57 UTC? The Meerkat control room made a deliberate gamble. A new machine learning filter trained to spot narrow comet-like signals in a sea of radio noise went live just minutes before the scheduled scan of 3I Atlas. The stakes felt high. Only weeks earlier, a false alarm from the older system had triggered a scramble. Solar interference had masqueraded as a discovery, and the team spent nearly 40 minutes untangling the error before retracting the alert. That episode forced a rewrite of the decision tree, and tonight every step was under scrutiny. As the clock struck 4:10, the console flashed a spectral anomaly warning. Two absorption lines perfectly spaced, each just over a kilometer per second wide. The algorithm confidence score ticked upward as it cross-checked the Doppler shift, minus 5.6 kilometers per second, a match for the predicted motion of 3I Atlas. Automated routines swept the terrestrial interference database. No match. Within seconds, the system flagged the event as low radio frequency interference likelihood and sent the alert to human review. The senior spectroscopist on shift leaned in, eyes on the spectrum. The lines were clean, narrow, and steady, no flicker from passing satellites, no telltale jump from a solar flare. A quick scan of the solar activity logs confirmed quiet conditions. At 4:12, the operator logged a manual override, marking the signal as an astrophysical candidate that meets cometary and geometric criteria. Protocol called for escalation. The operations coordinator paged 2 independent analysis teams, each tasked with pulling cross-polarization data and reprocessing the spectrum from raw visibility data. The room ran on adrenaline and habit. Every minute counted. The team knew that a misstep, another false positive, could undermine confidence not just in this result, but in the entire interstellar campaign. By 4:24, consensus was reached. Both teams found the same pair of lines, the same velocity offset, the same narrow width, no sign of instrument drift, no echo in off-target beams. The coordinator authorized a scientific alert to partner arrays requesting immediate follow-up from Green Bank, FAST, and the Very Large Array if geometry allowed. The chain of events was logged down to the second. Filter activation, detection, automated vetting, human override, multi-team confirmation, and external alert. The entire triage from first anomaly to partner notification took less than 15 minutes, less than half the time of the September false alarm. Inside the control room, the mood was tense but electric. The new algorithm had done its job, but it was the blend of software precision and rapid human judgment that kept the discovery on track. The team credibility, built on transparency and speed, would now anchor the story as the world astronomers turned their attention to a signal that just hours earlier had been buried in noise. The spectrum revealed 2 unmistakable notches: OH absorption lines at precisely 1665 and 1667 MHz. These were not just statistical blips or artifacts. Each line was narrow, just under 1.3 kilometers per second wide, and both were shifted by minus 5.6 kilometers per second, tracking the exact motion of 3I Atlas as it swept through the inner solar system. For a radio spectroscopist, these details matter. The width tells you how quickly the gas is expanding away from the comet, and the Doppler shift locks the signal to a moving real-world object, not a glitch or a stray echo from Earth. OH, the hydroxyl radical, is not a random choice. It is the direct product when solar ultraviolet light breaks apart water in a comet coma. The sun energy hits water, strips away a hydrogen atom and leaves OH behind. That is why in radio astronomy OH is the cleanest fingerprint for active water chemistry. Detecting it in absorption rather than emission means there is a cloud of OH gas blocking the background radio signal, soaking up photons at those exact frequencies. The depth and shape of the lines together with the known geometry let researchers calculate how much OH is present, and by extension how much water is being released. Thermal models cross-checked with ultraviolet and infrared data point to a near-surface temperature on 3I Atlas of 230 Kelvin, roughly minus 43 Celsius. At that temperature, water ice does not sit inert. It sublimates, turning directly from solid to vapor. The measured column density of OH, combined with the expansion velocity inferred from the line width, translates to a water production rate near 1 times 10 to the 27 molecules per second. That is a torrent of vapor comparable to some of the more active comets ever tracked near the Sun. The timing of the detection was no accident. Attempts in September, when the comet was farther from the Sun, found nothing. Only as 3I Atlas approached perihelion did the heating cross a threshold, triggering the sudden release of water and in turn the burst of OH. The narrowness and stability of the lines rule out local interference and fit the profile of a real expanding coma. The Doppler shift nudged the signal away from the worst of the solar radio background, opening a brief window where the chemistry could be seen directly. By tracing the photodissociation chain, water to OH to hydrogen, astronomers could for the first time follow the chemistry of an interstellar visitor in real time. The spectrum became a direct probe of the comet activity, not just a snapshot but a physical record of how sunlight, ice, and cosmic time interact on a body from another star. 9 degrees on the sky is the angular distance separating 3I Atlas from the coordinates of the legendary WOW signal of 1977 at the moment of radio detection. A sliver in astronomical terms, especially given the vastness of the sky. The coincidence is striking and it did not go unnoticed. Within hours, social media and science forums lit up with speculation, some drawing lines between the new hydroxyl absorption and that decades-old burst of unexplained radio energy from the direction of Sagittarius. Yet for researchers trained in the discipline of evidence, proximity is not proof. The 3I Atlas signal is chemistry in action, hydroxyl molecules absorbing at 1665 and 1667 MHz, the unmistakable signature of water being broken apart by sunlight. The WOW signal, by contrast, was a single unmodulated radio pulse, never repeated, its origin still debated. The only real connection is geometry, and even that is a product of orbital chance. As one comet dynamicist put it, spatial oddities catch headlines, but the real story is in the chemistry, not the coordinates. Still, echoes of the past linger. Surviving members of the original WOW team, including Jerry Amon, offered measured words to the press, recalling the lessons of 1977. Back then, excitement outpaced caution and speculation ran wild before the data could be fully vetted. This time, the mood is different. The Meerkat team, along with techno-signature researchers, stressed the need for rigorous cross-checks and a sober reading of the evidence. The hydroxyl lines are narrow, stable, and precisely Doppler shifted to match the motion of 3I Atlas, not the drifting patterns of artificial beacons or the fleeting spikes of terrestrial interference. Public fascination with the WOW field is understandable. The human mind seeks patterns, especially when cosmic coincidences evoke old mysteries. But in the world of radio astronomy, intrigue alone is not enough. The angular separation of about 9 degrees serves as a reminder. Sometimes the universe offers up compelling alignments that demand both curiosity and caution. Chemistry, not geometry, carries the weight of proof.